Okay, thank you, Mr. Chairman. My name is Lubomír Říha, and I'm presenting the work of me, Tomáš Brzo-Bohatý, Alexandros Markopoulos, Ondřej Meca, Michal Merta, and Tomáš Kozubek. So the talk is about the ESPRESO, which is our parallel FETI solver. If I kind of talk about the name, so the solver is has been developed by me, Tomáš Brzo-Bohatý. Then the mic acceleration is done by Michal Merta. The GPU solver is developed by me, and most of the numerical work has been done by Alexandros Markopoulos and Tomáš Brzo-Bohatý, while the preprocessing, the input and the output of the solver is done by Ondřej Meca. So if we talk about the solver, the solver, the ESPRESO, is implemented in C++. It's based on the MKL, and it heavily relies on the sparse direct solver. We use Pardiso most of the time, but we're also developing interface for MAMs right now, for the paysticks and different sparse direct solvers. Most of the time we use the Intel compiler, but it's not required. So when it comes to the parallelization strategies in the ESPRESO, we are having a hybrid parallelization, which means we can run a single MPI process per node and then use the threading. So we're using MPI for the threading. We are using a Cilk++. Plus we have a vectorization support, mainly achieved by the MK library, because a lot of the parts of the solver is based on the sparse and the dense blast routine from the MKL. If I talk about the hybrid total FETI method, so it is a non-overlapping domain decomposition method. So in this example, if we do the finite element discretization, we can decompose the problem into subdomains. That would be the FETI approach. In the hybrid FETI approach, we combine selected subdomains into a cluster, and we run in the solver. One cluster is processed by one MPI process, and then we do the hierarchical decomposition. We decompose into the clusters, and then the clusters we decompose into the subdomains. So the clusters are processed by the MPI processes. Yeah, I forgot to mention the FETI method was introduced by Farhad and Ru. The multi-level method was introduced by the Klavon and the Reinbach. So this is the work that we are based off. So why is the hybrid FETI scalable? So for the FETI, each subdomain has a rigid body modes. In a 2D, we have two translations, one rotations. In 3D, we have 3 rotations and 3 translations. So every subdomain adds its rigid body modes into the coarse problem. So if you have 1,000 subdomains in a 3D, you will have a coarse problem of size 6,000 by 6,000. And you need to invert this coarse problem because it is used by a projector, and it needs to be solved in every iteration. So in the hybrid FETI, we combine the subdomains into the clusters, and then we attach the clusters. We solve the clusters with the corners, which are the red arrows. We solve it exactly, we tied the subdomains in the cluster together, and then each cluster adds only 3, respectively 6, for 3D rigid body modes into the coarse problem. So this is the main reason why hybrid total FETI is scalable. It reduces the size of the coarse problem. So what is in the ESPRESO solver? So we implemented a total FETI. So we started with the total FETI to tune the communication layer, to tune the MPI processing, to see how we can optimize the stencil as well as the global communication. These are the techniques I'm going to talk about. ESPRESO implements a pipeline conjugate gradients in order to hide the global communication operations in the CG, and it also employs the parallel solution of the Coarse problem in the form that we built the explicit inverse of the Coarse problem in distributed fashion, so it's actually very fast. And then if we apply the projector, then we work with this distributed inverse matrix of the Coarse problem. We also implemented the hybrid parallelization even for the FETI. So for the FETI, instead of the cluster, we have a group of subdomain which are processed by the threads, which allow us to, even in case of the FETI, we can fully utilize the node. We can have, let's say, a couple of hundred up to 1,000 relatively small subdomains on a node, which is very suitable for the small problems if you want to run on the small clusters. You are not forced to use a large subdomains. Then the hybrid FETI solver takes the best out of all the techniques that we developed for the FETI, which is all the global communication, optimization, all the communications, plus the processing of the Coarse problem. It takes the best out of it and then adds the ingredient that reduces the Coarse problem size. And I'm going to actually show that the hybrid FETI can be used in kind of two approaches. You can have a configuration when you really want to go for tens or hundreds of billions of unknowns, and you can have a configuration that it's kind of tailored for smaller problems, let's say around 1 billion to up to 3 billions. So it is a different configurations which all suits better to these particular purposes. So in this slide, actually, I'm showing the implementation of the FETI. So the first difference is if we start with the gray line, which is the FETI with the regular conjugate gradient, then the yellow line is actually the performance benefit we get by using the pipelined conjugate gradient, and the red line is the benefit that we get by using the parallel explicit inverse of the Coarse problem, which also, in our case, against to the original implementation, reduces two global communication, which was gather and scatter into the single call of the MPI, which is all gather, which plus it also parallelized the processing of the Coarse problem, which gives us the biggest benefit, as we can see here. So this is actually the real behavior. What would you get if you go from one node, which is here, to 155 node, and you have fairly large number of subdomains per node, let's say in order of several hundreds of subdomains. So if you go to the 125 node, your preprocessing, which in this case means assembling of the Coarse problem and its inverse, it's exponentially growing, which is at some point it doesn't fit into at first it's slow and then it doesn't fit into the memory. While you see the hybrid FETI, which kind of keeps the preprocessing time at the minimum. You see it adds some constant, which we call the hybrid FETI preprocessing. It's assembling of the objects for the cluster, the object that kind of holds the clusters together. So this is a constant addition, but the assembling of the FETI Coarse problem is then very fast. So we have two approaches how we speed up the Coarse problem processing. So this first one is to assemble the Coarse problem. So Coarse problem is a global object, but it can be assembled in a nearest neighbor fashion. You really need just to extend the natural Coarse matrices between the neighbors, and the neighbors can calculate these blocks of the coarse problem. So the gray one, the gray block would be in case of the linear elasticity in 3D. The gray block would be in this part would be a matrix 6 by 6, 6 rigid body modes by 6 rigid body modes. Then you can calculate the coarse problem on the MPI process, which is shown here, and then every MPI process sends and we're using the binary reduction actually to assemble this global coarse problem matrix. So every node sends in a binary tree reduction kind of sends its part of the coarse problem matrix, and finally when the root, the MPI process number zeros will get this entire matrix. Well, the other way we would do it, that you would collect all the coarse natural coarse problems matrices, the matrices G, and then you will have to multiply this matrix by its inverse, by its transpose, which we tried at the very beginning, but when you get to the large matrices, it's very slow and it doesn't even fit into the memory anymore. So we have this distributed approach where every MPI process calculates a very small part, and then all the parts of the coarse problem matrix are assembled at the root node. Then actually what we do once we collect this coarse problem matrix on the root node, we broadcast it to all the compute nodes. Then each compute node calculates the factorization, and then it calculates its part of the inverse matrix of the coarse problem. So the factorization is usually in this step the longer, but we are still talking in a few seconds to get the factorization. And then actually, if we would calculate the inverse of the matrix on a single node, that would be the most time-consuming part, because we have to solve a very large number of right-hand side. But then, since each MPI process in hybrid FETI solve for only 6 right-hand sides, then the solve extremely fast. It's actually very negligible. So we calculate the inverse matrix of the coarse problem with the help of all the compute nodes that we have, and it ends up that each compute node has only the part of the inverse of the coarse problem that it needs. So then the application of the projector, it's really that we collect the rigid body modes from in every iteration when we apply the projector, we collect the rigid body modes from all the clusters. This is the MPI altogether, which is here. Then we use the local parts of the inverse matrix, and the only global operation here is actually the altogether. After that, there is no operation, and each node can continue the CG solver in parallel. So we investigated for the paper. We investigated what is the optimal configuration of the hybrid FETI. So in terms of how should we configure the clusters, how big should be the clusters. In this first slide, we show the memory efficiency. So this is pretty much evaluation for a node where you have dual socket with 12 core, each socket 12 core, and 120 gigabytes of memory. This is, for example, the machine that we have at IT for Innovations. So this evaluation is if we use the clusters of different sizes in here. So we see that if we use small clusters, let's say we use 12 clusters, each of size 680,000 unknowns, then the efficiency of the cluster per gigabyte per gigabyte of memory is 140, let's say 43,000 of unknowns. So this is when you use a small clusters. You have one cluster per core, which means that you're running 12 MPI processes per socket. On the other hand, you have a cluster which is the least efficient. That's the cluster which has 7 million unknowns. And you can see that the memory-wise, it is the least efficient. That's because the hybrid FETI objects are getting larger. So if you don't have to use thousands of clusters, and you know that you need only use 2, 3, 4,000 clusters or up to 8,000 clusters, you can very efficiently run 8,000 MPI processes, where each MPI process will work on the one cluster, and each cluster will sit on one CPU core. And that would be the most memory efficient way how to use it. And this is, for example, this is, as I said, one configuration that we use. The other extreme would be the large clusters. And that's what we have to use if we run the test on an entire machine of, let's say, 10,000 of compute nodes. Then the other optimization is for the single iteration time, and this really tells us what decomposition should we use, how many subdomains should we use on the cluster to get the fastest single iteration time. So it always shows that it varies between, let's say, for this it's 340, and for the largest cluster, 7 million, it's about 1,000 subdomains per cluster. So this is the range that we get for the clusters of different sizes, so depending how big clusters we want to use. So this is the first set of results actually we showed in the paper. So I just want to use this figure. This is actually running on the EPCC Archer machine, and it's solving up to 30 billions of unknowns on 4,000 nodes of the Archer. So if I show results like this, I have usually the stiffness matrix factorization, which is a local operation. You just have, for each subdomain, you have to factorize the matrix. Then we have the hybrid FETI preprocessing, which is strictly a preprocessing related to the hybrid FETI method that is also happening on a single node. There is no communication between the nodes, so it is still embarrassingly parallel in between the nodes. Then we have the FETI preprocessing time, which is actually calculating the Coarse problem, assembling the Coarse problem, and calculating the distributed inverse of the Coarse problem. And then, in this case, the most time-consuming part is the iterative solver step, which is the conjugate gradient solver in the FETI. So, for example, in this test, we see that the iteration time is about 1.5 seconds. We were able to solve the problem in 170 iterations, the largest one, and the iterative solver took 265 seconds to perform these 170 iterations. While the preprocessing was, again, the factorization was 17%, the hybrid FETI preprocessing was 17 seconds, the hybrid FETI preprocessing was 9 seconds, and the FETI preprocessing was 10 seconds. You can see that actually going from 1,300 to 4,000 node, even the FETI preprocessing kind of scales. It doesn't add any additional time. So in this graph, I would like to show how the hybrid FETI actually performs compared to the FETI. So I have three configurations here. I have a total FETI, the two-level FETI with the small subdomains, which means I have a large number of subdomains, which means that the FETI preprocessing, the Coarse problem, assembling and inverse, it doesn't scale at all. Then I have the other extreme where I have a total FETI with large subdomains. So I have one subdomain per core, and in this case I have up to 100 subdomains per core for this problem. And then I have the hybrid FETI in between, where I have even smaller subdomains than in case of the FETI, and you see that this reduces the factorization time of the stiffness matrix, but it adds the hybrid FETI preprocessing. But on average, this is about the same as if we have a preprocessing for the total FETI. Then the FETI preprocessing time, you see that it scales much better. It actually scales even better than for the FETI with the large subdomains. So, and then the iterative solver, of course, in case of the hybrid FETI, since it is a multi-level method, the number of iteration is higher. But since we are working on very small subdomains, the single iteration time is significantly faster, and it reduces the overall iterative solver time. So this is the configuration for the small problems. This is for a 1.7 billion of unknowns. And you can see that even in this case, even though for the very small problems the total FETI is better, the hybrid FETI it scales much better, and for certain problems it becomes more efficient than the total FETI. Even for the small problems, you don't have to go to tens of billions of unknowns. So this part, I guess I'm going to skip it. So the next, I have another set of results which wasn't presented in the paper because they were measured recently. So for most of the large-scale tests, we're using this problem generator. It is a massively parallel benchmark generator which runs in parallel, and you don't need any communication. Well, you need some communication. You don't need an extensive communication to assemble the problem. It takes several seconds to assemble the problem of hundreds of billions of unknowns, as far as we tested it. It is a sphere or a cube benchmark, and it supports the linear elasticity or a heat transfer or the Laplace equation. So we have several tests on the Pitts-Dane. So this figure shows a strong scalability of the hybrid FETI method on the Pitts-Dane. The first graph, this shows the single iteration time. This graph shows the conjugate gradient solver runtime, which includes all the iteration, plus it includes the including conditioning of the problem when you decompose it into the small and smaller subdomains. So this is a test that solved 2.6 billion of unknowns on up to 5,000 nodes of the machine that I believe everybody here knows very well. We also have access to the Titan machine, which allows us to run a significantly larger test. Unfortunately, for us, Titan has only 32 gigabytes of memory per node, which kind of, for our solver, having a large amount of memory means being able to solve large problems. So Titan has only 32 gigabytes of memory per node. If it would have 128, we would be able to solve almost 4 times larger problem. But if we start with the strong scalability test, so this is a strong scalability of 11 billion of unknowns running from 2000 to up to 17,000 compute nodes. So this is the linear scaling, and you can see that the solver achieves a superlinear scalability.
Is that because of the n cubed?
Yes, it's partially, but partially also because if you have smaller subdomains, you're doing less iterations, and then the sparse direct solver performs way better on the smaller domains. So the mixture of these. So this is on the solving the heat transfer. Again, a strong scalability for 20 billions of unknowns. Again, you see we achieve a superlinear speed up. So then the weak scalability test on the Titan. This is again the heat transfer. We get a better larger numbers with the heat because the matrix and its factorization needs smaller amount of memory, so we get a better problem. For the linear elasticity, well, let me get back to it. So we have, in this case, we're solving 124 billions of unknowns again on the on almost entire Titan machine, 17,576 compute nodes. And we see that this is the preprocessing time, which is mostly caused by the hybrid FETI preprocessing, but that scales again. That doesn't get worse when you're scaling up. Plus, the preprocessing small amount down there is the FETI preprocessing, which is almost negligible in this case. The number here is a number of iterations, And then the light bar is the iterative solver runtime. So we also did some tests on the Salomon machine. For this particular test, we use the real-world geometry generated from the ANSYS. This is a 30 million unknown problem of a linear elasticity, and you see that the number of iteration here is significantly larger because it's a fairly complex geometry, going from 1,000 down to 365 by pretty much making the subdomains smaller and making clusters smaller. Okay, yeah. So, okay, very briefly, I just want to show that the ESPRESO also supports the accelerators. We have a support for both GPU and Intel Xeon Phi. So, since the accelerators doesn't work very well with the sparse matrices, we have to convert the sparse stiffness matrices into dense local Schur complements. So we calculate the local Schur complements for each subdomain, and then we use the Schur complements on the accelerator. Yeah, so this is actually the three approaches that you can have. So this is in the operator multiplication with stiffness matrix. For the FETI, it means that you do the sparse multiplication with the constraints matrix B, then you do the solve with the sparse direct solver, and then you do the sparse matrix vector multiplication with the transpose of B. And then you need to exchange the data across the interfaces. So if you want to use the Schur complement, you would have to calculate this Schur complement, and then then you don't have to perform the sparse matrix multiplication, and then instead of going the sparse direct solver, you use the dgem on either CPU or GPU or mic. The method is the same. So this comes with a price in the form of the preprocessing time. The preprocessing time is longer, but then the single iteration time is shorter. So I have a results for the mic. This is comparing two Haswell on the Salomon machine to the two Intel Xeon Phi, and we can see that we reach the speed up over 2.5. And this is actually running the entire solver, the hybrid FETI solver, on up to 443 nodes. We can see that we can get the speed up to 2.7 if we use the Intel Xeon Phi accelerator, which use the Schur complement. And this is the same results on the GPU. We can again see that we have a speed up over 3.5 on the Titan machine if we use the GPU. But compared to the previous test, the Titan is using fairly old AMD Optron, while the Salomon has two Haswell processors. Yeah, so to conclude, I was presenting the ESPRESO Solver, which contains the optimal global communication in form of the pipeline conjugate gradient method, the parallel solution of the Coarse problem. For the hybrid parallelization, we use the threading, and for the FETI, we combine a group of domains. We don't calculate them as a cluster, but as a group of domains, and we can process multiple hundreds or thousands subdomains on each node, which allows us to use a fairly small subdomains. So we show that the solver scales up to the full range of the second world largest machine, and that we also support the GPU and the Intel Xeon Phi acceleration. Thank you.
Thank you.